All right, we're going to take a look at, let's see, this problem. It says a 24-kilogram child descends a 5-meter high slide. So this is the child on the slide problem. Reaches the ground with a speed of 2.8 meters per second. There is friction. They wanted to see an LOL diagram for at the top, halfway down, and at the bottom of the slide. And they want to know how much energy was transferred into another kind of energy due to friction. What form of energy is that going to be transforming into because of friction, folks? You say that's going to be turning into thermal energy. So I want to know how much energy got transferred into thermal energy because of friction. You're like, well, the energy transferred into thermal by friction. You say, oh, that's the work done by the friction force. That's what we'll be calculating. Okay, so that's what we're going to do. Okay, so hey, to start with, they want the LOL diagram. I'm going to start by making a sketch. Okay, it's always like a good way to start a physics problem, right? So we have this slide. Okay, and the child's going to go from the top of the slide to the bottom of the slide. And as she does that, let's see here, we know that the mass of the child is 24 kilograms. We know that they tell you the slide is 5 meters high. So we're going to say that that's the height change here from the top to the bottom here, 5 meters. And we know that at the end of the slide that the speed is, they tell us 2.8 meters per second. 2.8 meters per second. Okay, we're assuming that we're going to start from rest. So 0 meters per second there. Okay. And they want to know the energy transferred due to friction from here to here. Now, they told us there's some locations, though, that they want us to do LOL diagrams for first. And so they tell us they want us to look at position A being the top of the slide. Call that location A. Location B, halfway down the slide. And then position C is at the bottom of the slide. Right. Call that position C. Okay, so first we'll do the LOL diagrams. And again, the purpose of this is just to give us an overview of what's going on as we go from position A to position B to position C. So first we're going to identify our system. And we said, well, clearly we want the child. But then you start asking, are there other things we want to expand the system and include? And so to do this, I usually start thinking about force diagrams. Now, as the child slides along from the top to the end, you're like, what forces will be acting? I'm just going to do kind of a general diagram for the child partway down, sliding along the slide. All right. And you say, what forces are acting? You say, well, there's a gravitational force. That's the only ranged force. Contact force is the only thing touching the child is the slide. Are they pressed together? You say yes, so there'll be a normal force sticking straight out of the surface. And then you say, are the surfaces sliding past each other? Yes, so then there's friction. Opposing the slide, kinetic friction. And that's it, that's our force diagram. So now I think about it, and I'm like, okay, my system is going to be the child. Do I want to include other things? Well, what's interacting with the child? And you really see there's just two things. There's the Earth pulling down gravitationally, and there's the slide, which is pushing up on her, and friction with the slide pulling against the slide. So first of all, do we want to include the Earth in the system or no? If we include the Earth, then this force would sort of go away, the gravitational force, because it would be a force inside the system. And that would mean that we could have gravitational potential energy terms, which is a good thing, because if I don't do that, I'd have to be doing work terms for gravity. And since the angle of the ramp is changing all the time, the angle of our motion and the angle of the gravitational force would be changing all the time, and trying to calculate the work term would be messy. As in, we don't know how to do that because we don't know the exact shape of the curve and so on of the slide. So we are going to have to use gravitational potential energy instead of doing a work term. In other words, we're going to have to include the Earth in our system. We have no choice, right? Because we can't calculate that work term because of the way that angle's changing. Okay, so child and Earth. Do I want to include the other thing interacting with the child, the slide? Well, if I do that, then I won't have any outside forces. I won't have any work terms. And then that would mean that I won't have any energy transfer. But I know that there's going to be energy being converted into thermal, and I wouldn't have any way of calculating it. So it's better off to make this slide be something outside the system so that this friction force is a force from outside, so it'll be a work term that would be, that thermal energy being produced. So yeah, I'm going to do just a child and the Earth as my system. Child and Earth. There we go. All right. So when I do this then, let's think about different energy types. Oh, sorry, first energy transfers. So the only outside forces now are friction and the normal force. The friction force is going against the motion, so it will be doing work. The normal force is going perpendicular to our motion at all times, right? Going straight out of the slide. And so that's not going to be doing any work. So it's just that friction force. It is acting through the entire path, taking energy out. So we will lose some energy. I'm going to draw an arrow leaving. This is work done by friction. And I'm going to lose some energy here too, work done by friction. It's going to be acting against us all the way from A to B and from B to C. All right. But again, normal force isn't doing any work because it's perpendicular to the motion, and gravity isn't doing work because it's inside our system. So that's it. That's our transfer diagrams. Now we worry about which energy types we want to put into our sketches there, into our energy bar graphs. So we just kind of run down the list, right? And like, okay, what about kinetic energy? We only need to include it if it's changing. Are we changing speeds? Yes, then we're changing kinetic energy. We would want to analyze that. What about gravitational potential energy? You say, yes, we're changing heights, and we're including the Earth, so we can have UG. Elastic, we don't have anything stretching. Chemical, no chemical reaction. Thermal, well, I'm going to basically say that that is the energy that's going to be, that's the form the energy is going to be converted to by this friction force. So I'm going to be taking care of it by the work done by that friction force. That's going to take care of that for me. So this is it. I have kinetic and gravitational potential, and that's my diagram. So do I know, is there anywhere where I know the kinetic or the gravitational potential energy are zero? So first, kinetic energy, you say, yeah, kinetic energy is 1/2 mv squared. So when the velocity, or the speed, I should say, is zero, the kinetic energy will be zero. You say that happens at the start. We're starting from rest. So this here is going to be zero. But we are moving as we move along and getting faster and faster. So I'm going to have more and more kinetic energy as we go. What about gravitational potential energy? You say, well, for gravitational potential energy, you need to decide the location, the configuration you're going to call the zero potential energy arrangement. Usually people like to call the lowest position on a problem height zero, and that's where the potential energy is zero. So let's do that here. Let's go ahead and call this height at C. We'll say that that's the zero height. Then my gravitational potential energy, since it's m times g times h, that'll be zero there. And I think that's all the zeros that we know. So at this point, you say, well, can we calculate any of these? And you say, well, sure, we've got some information here. We could calculate gravitational potential energy. But again, I don't want these LOL diagrams to be like super precise. That's not my goal here. My goal here with the LOL is just to get an overview of what's happening. So I'm just going to go ahead and choose a value for UG. It's clearly not going to be the correct value. That's okay. I'm just picking a value. I'm just going to say that we have 12 units of gravitational potential energy at the start. Now, let's go to and we've got zero kinetic. So the total energy of the system here is 12. When we go from A to B, is any energy entering or leaving the system? You say, well, sure, look, there's some work done by friction. It's taking some energy out. So my total here will not equal the total here. But I do know a value here. I can figure one out because they defined position B, they said, was at half the height of the top of the slide. Well, if the energy here is 0, the energy here at half the height would be half the energy. I had 12 units of potential energy at A. I have to have 6 units here at B. Now, the total energy here was 12. Is the total energy here 12? No, because some energy left. So my kinetic energy here, it's definitely not 0. We're moving. So it's going to be somewhere between 0 and 6. All right? Let's just go ahead and say that it's 4 units. All right? Well, I had 12 units of energy here, 10 here. I've lost 2 units. That must be the energy that was taken out by friction. All right, now, clearly this 12 was a number I made up, but I knew whatever this number was, the UG at B has to be half that. And I knew that I'm going to have some kinetic, but some energy leaves the system. It's going to be taken away from that kinetic sum. So it's, but how much I put here, this was kind of arbitrary. I chose to do 2 units, leaving 4 in kinetic. That was kind of an arbitrary choice of mine. All right, I don't really have a good feel for how rough this slide is. They haven't given me any information about it. I don't know how much energy, what fraction of the energy really is being taken out. I just kind of picked some values. Okay, what about between B and C now? Well, that friction force is going to continue acting, taking more energy out of the system. I know that when I get down to C, I'm at height 0, right? My total energy here was 10, but I'm going to lose some. So I'm not going to have 10 units of kinetic there. I'm going to have somewhat less. I know that I have some kinetic energy at the end. It doesn't all go away. I don't get stopped. The child is still moving as they go off the end of the slide. So I'm going to give them some kinetic energy here. I'm just going to say they have 2 units of kinetic energy there. So here I have, that's a lot. Wait, 2, I'm sorry. Changed my mind. Let's say they have, we'll say 8 units of kinetic energy there. Sorry about that. That's quite a difference. Sorry about that. Okay, let's say they have 8 units of kinetic energy there. So my bar graph is going to go all the way up here to 8. So at this point then, what's the total energy of my system? 8 units. I had 10 here, 8 here. I've lost 2 more units to work done by friction. All right, and so that's what that looks like. Sorry, the whiteout is wet. Otherwise, I'd continue the bar, but this is one big bar up to 8. All right, so that's my LOL diagram. Again, I did kind of choose, arbitrarily some values here. In hindsight, maybe I'd make a little bit more kinetic energy be taken out. Nah, I'm good with this. I'm good with this. Okay. All right. Then that's it. Okay. Hey, what do we do now? That's it for the LOL diagrams. They want now us to figure out how much energy was taken out by friction. Now, clearly, in our little example here, we took 2 and 2, 4 units out, but they mean in reality with the real values. So we need to recognize that energy removed from the system by friction, that's the work done by friction. That's really what they're asking us to solve. Okay, again, we're going to go overall from A to C is what they want to know, the energy taken out from A to C. Okay, so for the overall process, so I'm going to be analyzing this going from position A to position C. We're going to use the work energy theorem. Sigma W is delta K. And because I'm including the Earth in the system, I can have a delta UG. Okay, the gravitational force, it's like it's not on our diagram. I mean, it's there, but it's between parts of the system. It's an inside force, so it doesn't show up. So we really would just have that friction and that normal force. Work by friction, work by normal. Delta K is the K at the final minus initial when we do deltas. I'm going to call that the final is at C. So I'll say the K, kinetic energy at C minus the kinetic energy at A. Final minus initial. Plus the UG at C minus the gravitational potential energy at A. All right. So that's the way I'm going to set that up. Are some of these terms 0? You say yes. Okay. Some of these terms are definitely 0. You say, hey, I recognize that friction force is doing work. It's pushing against the motion as we slide along. But what about the normal force? That's perpendicular to the motion. It doesn't do any work because N is perpendicular to the motion, always, right? It's sticking straight out of the ramp and we're going along the ramp. Kinetic energy at C, we definitely have some. We got some speed there. Kinetic energy at A, well, we're starting from rest. So the kinetic energy of A is 0 because the V at A is 0. Gravitational potential energy at C, well, we called the height at C 0, so that UG at C is 0. Why? Because the height at C is 0. That's why that's 0. And the UG at A, we definitely have some there. So when I get rid of the 0 terms, this equation, simple, this long looking equation simplifies down to just be the work by friction is equal to the kinetic energy at the end minus the potential energy at the start. So that difference in the energies, potential we started with and the kinetic we end with, that like missing energy is the energy that left, that got turned into thermal by that work by the friction force. It's the energy that left the system converting to thermal. So there we go. We're trying to solve for this work by friction. That is the thermal energy that's generated. So we just need to solve this side. Kinetic energy is 1/2 mass times speed squared. Gravitational potential energy, whoops, is mass times the field strength times the height. We're subtracting that, I apologize. Let's tidy that up. There we go. All right. Taking a look at this then, you say, well, do I know a value for the mass? You say, yeah, we know it's 24 kilograms. Do we know the speed at C? Yeah, 2.8 meters per second. Do we know the field strength? 9.8. Do you know the height at A? Yes, 5 meters. We know everything we need to know to do the calculation. Put in our values, 1/2, 24 times 2.8 squared minus 24 times 9.8 times 5. Okay. We put that in our calculator and get our value. Okay, and so I'm getting a negative value here, negative 1081.92. Let's say joules. You say, do we want to have a negative there? You say, well, yeah, negative because we are losing energy. Energy is leaving the system, right? Going out into the environment. Okay, the system's losing energy. It's going out to the environment. You say, because that friction force is acting against the motion. It's trying to slow you down. And so the kinetic energy I have at the end is less than the potential energy I had at the start. I'm going to get a negative value here, and that makes sense. That means the energy is leaving the system. So that's it. That's the work done by friction, and that's how much energy was transferred into thermal by friction. All right.